In Module 6 of Chapter 20, we'll be looking at the Sharpe ratio and how it applies to Ito processes. We've seen the Sharpe ratio earlier in a simpler context, and now we'll study how this notion gets applied when we're talking about Ito processes, and in particular processes associated with stock prices. Let's recall a few definitions. If we have an asset with an expected return of alpha, the risk premium is the excess of alpha over the risk-free rate. So here R is the risk-free rate, and the risk premium is always defined as the excess of the expected return over R. The Sharpe ratio is then defined as the ratio of the risk premium to the standard deviation. In a sense, the Sharpe ratio tells you how many units of excess return do you get for every unit of standard deviation that you take. That's what a Sharpe ratio is. It's the number of units of excess return divided by the number of units of volatility. So you can think of it as a unit measure. It's the excess return per unit of volatility. We can use the Sharpe ratio to compare two perfectly correlated claims or two perfectly correlated assets. And the reason is that if two assets have perfect correlation, they must have the same Sharpe ratio. Now notice, I'm not saying that if two assets have the same Sharpe ratio, that they must have the same return or the same standard deviation. Indeed, they don't need to. And all that you can say is that if they have the same Sharpe ratio, then in fact, sorry, I'm going to just back that up. I misspoke. What you can say is if they're perfectly correlated, they must have the same Sharpe ratio. You cannot say that they have the same mean or the same standard deviation, but that the relationship between the means and the standard deviations to produce this must produce the same Sharpe ratio. And if that's not the case, we can have an arbitrage opportunity. And let's see why. Imagine that we have two perfectly correlated assets, S1 and S2. They have means, mu1, mu2, vols, sigma 1, sigma 2, and they have a perfect correlation, rho is 1. So again, note that we're not saying the means are the same or the variance is the same. So imagine that asset 1 has a bigger Sharpe ratio. What we're going to do is we're going to create an arbitrage. Namely, we're going to create a portfolio that costs us nothing at time 0 but gives us a profit. And in doing so, what we're going to do is we're going to buy 1 over sigma 1 S1 shares of S1. So imagine that, so this is what we're saying, that if, as an example, if S1 was worth $100 and it had a sigma of 20%, then the number of shares we're going to buy is 1 over 0.2 times 100. And 0.2 times 100 is 1 over 20, so it's 1 over 20. So we're going to buy 1/20th of a share. 1/20th of a share, and so that's the goal. And the reason for this fancy formula, as we'll see in a minute, is this is what's going to allow us to convert our returns back to the Sharpe ratios that we're arbitraging. So if we, in this example, we would buy 1/20th of a share, and we would spend $5 on shares. And similarly, we're going to buy 1 over sigma 2 S2, that many shares of the S2 stock. There's going to be a cost associated with that, because in general, the number of shares we're buying won't have a cost of 0. It might have a cost, or it might produce a cash flow for us. Either way, we're going to make the adjustment in T-bills, that the cost, which is 1 over sigma 1 minus 1 over sigma 2, that cost or dollar amount will either be provided by shorting T-bills or will invest it in T-bills, depending on whether it's positive or negative. I don't care. All I want to assume is that that cash flow earns the risk-free rate.